look up at a cloud today, and I mean, you just see peaceful scenery, right? Like a painted backdrop drifting lazily by.
Yeah, exactly. It's just part of the sky to most of us.
But the thing is, you are actually looking at, arguably, the single greatest threat to the accuracy of modern climate science.
It really is this ultimate paradox. I mean, the thing we associate most with a calm, lazy afternoon is actually this hyperactive, just incredibly complex engine of thermodynamics.
Right, and we take this massive churning machine and we just dismiss it. Which is why today we're taking a deep dive into an excerpt perfectly titled, "Look Out the Window on Almost Any Day and Theirs." And our mission for this deep dive is to shortcut you, the listener, to being completely well-informed about the hidden physics of clouds.
We want to take them from being just background scenery into, well, the single most fascinating puzzle in Earth science right now. Exactly. Okay, let's unpack this, because before we can understand how they are literally breaking the world's most advanced climate models, we have to shift our focus to what a cloud actually is at a fundamental level. We need to talk about the invisible ingredients.
Right, and the primary ingredient is already all around you. Like, the air you are breathing right now holds water, not as liquid drops, obviously, but as an invisible gas, water vapor. And the main rule governing this is that temperature dictates capacity. So warmer air has the energy to hold a lot of this invisible vapor, but cooler air holds significantly less.
Which brings us to the saturation point, right?
Yes, exactly. When air cools down, its capacity to hold that water vapor just shrinks. And eventually, it hits this specific temperature threshold where it's completely full. Like, it cannot hold a single other molecule of gaseous water.
That's the saturation point.
Right. And because that excess vapor has to go somewhere, it undergoes a phase change. It condenses out of that invisible gas state and becomes liquid water droplets. Or, if it's cold enough, ice crystals. So this makes intuitive sense. I mean, it's the classic cold glass of lemonade on a sweltering summer day.
Oh, yeah, perfect analogy.
Right, because the ice-cold glass chills the warm summer air immediately surrounding it. That localized pocket of air drops past its saturation point, its capacity shrinks, and the excess water vapor just, it condenses into sweat on the side of the glass.
It does, but, and this is key, the lemonade glass provides a crucial element there. It provides a surface.
Okay, surface.
Yeah, because out in the open sky, water vapor is remarkably stubborn. Even when the air is super saturated and desperately needs to unload excess water, the vapor actually struggles to condense on its own.
Really?
Yeah, it requires a physical scaffold to cling to, otherwise it often just remains a gas.
Wait, so in the sky, pure water vapor is just floating there, refusing to turn into a cloud unless it can grab onto a speck of dust. I mean, if the sky is mostly empty space, where is it finding a surface?
Well, that's the thing. The atmosphere is actually brimming with microscopic solid surfaces. We call them condensation nuclei. And we are talking about ultrafine sea salt whipped up from the crests of ocean waves, or microscopic soil particles blown from dry deserts.
Wow.
Even ash and soot from forest fires. Trillions upon trillions of these invisible specks are constantly suspended in the air up there.
But wait, if the atmosphere is completely loaded with trillions of these condensation nuclei at all times and water vapors everywhere, why aren't we just surrounded by a permanent global fog down here? Like, why isn't the entire planet just one giant cloud?
Because the presence of the dust scaffolds isn't enough on its own. The air temperature still has to drop low enough to force the vapor out of its gaseous state.
Oh, okay.
Down here at ground level, the air is usually warm enough to easily hold on to its vapor. To get a cloud, you need a mechanism to drastically cool a massive volume of air.
Which brings us to the giant refrigerator in the sky. Or, well, rather the lack of one. Because if there's no massive cold object chilling the air like our lemonade glass, how does the sky drop below that saturation point in the first place?
Right. It happens through this thermodynamic phenomenon called adiabatic cooling.
Adiabatic cooling. Okay, explain that.
So adiabatic simply describes a change in temperature that happens without any heat being exchanged with the surrounding environment.
Wait, what?
Yeah, there's no cold front swooping in to chill the air, and it's not touching a freezing surface.
Cooling without touching anything cold. I mean, that sounds like a physical contradiction.
It does, but think of a parcel of air as a giant invisible balloon. As that balloon rises higher into the atmosphere, the ambient atmospheric pressure around it drops.
Because the air is thinner up there.
Exactly. There is simply less air above it pushing down, and because the outside pressure drops, the balloon naturally expands outward.
But expanding takes physical effort, right? Like it has to push against the air around it.
That is the absolute key. Pushing against the surrounding atmosphere requires work. The air parcel has to spend its own internal thermal energy to push its boundaries outward.
Oh, I see.
By expending that internal heat energy to expand, the balloon's overall temperature plummets. It cools itself purely through the mechanics of its own expansion.
The perfect everyday analogy for this, I think, is a bicycle tire. Like when you let the air rapidly out of a highly pressurized bike tire and put your finger near the metal valve, that rushing air feels freezing cold.
Yes, that's exactly the same physics.
And it isn't because the tire was stored in a freezer. It's because the air is expanding rapidly as it hits the lower pressure of the outside room. It is literally burning its internal energy to expand, and it drops in temperature as a direct result.
Precisely. Now just scale that bicycle tire effect up to a massive column of rising air. It rises, the ambient pressure drops, it expands, and it cools.
Here's where it gets really interesting. Because this cooling is driven by consistent physical laws, it creates visual boundaries we can actually see in the sky, right?
We can.
As that massive air bubble rises and cools, it eventually hits the exact altitude where its temperature drops past that magical saturation point. And you can see this invisible threshold drawn across the sky.
You're referring to the flat bases of clouds.
Yes. Like when you look at a field of fluffy clouds and the bottoms are completely flat, like someone just sliced them off with a laser level.
Yeah, it's striking when you really notice it.
That flat base isn't a coincidence, is it? It is the visual evidence of the exact altitude where the expanding air finally got cold enough for the water vapor to grab onto the dust scaffolds.
It really is a literal line of atmospheric physics made visible.
That's so wild.
Below that flat line, the air is expanding and cooling, sure, but it's still warm enough to hold its vapor. But the millisecond it crosses that altitude line, the temperature drops below the threshold, condensation occurs instantly, droplets form, and a visible cloud appears.
So the expansion cools the air, and that forms the cloud. And this is the next logical step. What initiates the rising? Like what pushes the air up to expand in the first place? And how does the way it's pushed alter the physical shape of the cloud we see?
Well, the mechanism of the upward push dictates pretty much everything about the cloud's architecture. Take the sun, for instance. It heats the Earth's surface unevenly.
Unevenly.
Yeah, so a dark plowed agricultural field absorbs way more heat than, say, a lush green forest sitting right next to it.
Ah, okay. So the air directly above that plowed field gets much hotter than the surrounding air.
Right. And that heat creates localized, highly buoyant pockets of air that just shoot upward, almost like an invisible hot air balloon. When air is pushed up vigorously in these tight, localized columns, it builds vertically. And this creates cumulus clouds, which actually comes from the Latin word for a heap or pile.
The classic fluffy ones.
Exactly. These are your classic cotton wool clouds with those flat bases we just talked about, and puffy, bubbling tops that reflect that really forceful upward boiling of the air.
But what happens when that upward push isn't a tight, localized column? Like, what if an entire region of the sky is being lifted slowly?
Then you get a completely different structure. This often happens when two massive weather fronts collide, forcing a huge, broad wedge of warm air to slowly slide up and over a denser, colder air mass.
Okay, so a much gentler lift.
Very gentle. Because the rising is gentle, widespread, and stable over hundreds of miles, the resulting cloud spreads out in a massive, continuous layer.
Which are?
These are stratus clouds. Stratus is Latin for spreading out. That's your typical overcast day, just a featureless gray blanket covering the entire sky.
The source material also mentions terrain as a trigger, or a graphic lifting, it called it.
Oh, yeah. That occurs when a fast-moving wind hits a massive physical barrier, like a mountain range.
Right, because the air can't just go through the rock.
Exactly. The entire mass is forced violently up and over the peaks, and this forced lifting can create those really dramatic lens-shaped clouds that hover over mountains or trigger massive precipitation on the windward side of the range.
And if the upward push is just unimaginably powerful, regardless of what triggered it, it just keeps building upward, right?
Oh, it builds up to incredible freezing heights. A vigorous cumulus cloud can just keep feeding on hot, moist air, expanding and rising violently until it becomes a cumulonimbus, the classic thunderhead.
Those look so intimidating.
They are. These monstrous clouds can reach all the way to the upper boundary of the troposphere.
Which means it gets so cold that it completely changes the composition from water droplets to ice crystals.
Hmm?
And that explains cirrus clouds too, right?
It does. Cirrus clouds form so incredibly high up that it's far below freezing, and fierce upper-level jet stream winds stretch those ice crystals into wispy hair-like curls. Actually, cirrus is literally Latin for a curl of hair.
I love that.
Yeah.
So the physical state of the water and the sheer force of the wind at those extreme altitudes completely change the visual texture.
Exactly. Every single cloud shape you see is basically just a physical record of how the air was lifted and how cold it got.
That makes me think about fog. If a cloud shape is just a record of atmospheric physics, and fog forms when the ground loses heat overnight, chilling the air right above it until it condenses, does that mean when you're walking through a thick morning fog and you feel that mist on your face, are you literally just wandering around inside a ground-level stratus cloud?
You are. In every meaningful physical sense, fog is a cloud on the ground.
That is wild to think about.
It's true. The mechanics of vapor, the dust scaffolds, reaching that saturation threshold, it's all completely identical. The only real difference is the lifting mechanism.
Right, because there isn't one.
Exactly. Instead of the air rising to reach cold temperatures, the cold temperatures came down to meet the air at the surface. So you were experiencing the inside of a cloud without ever leaving the pavement.
It's almost unsettling when you realize we live our daily lives wandering through the exact same physical mechanisms that dictate the sky. But, and this brings us to the real crux of the issue, we've decoded how clouds form and why they take these different shapes. It's lovely descriptive science. But why does this basic recipe make clouds the ultimate headache for climate scientists?
Well, it's because clouds play a massive, dual, and heavily contradictory role in the Earth's energy budget.
The energy budget.
Yeah, the energy budget is essentially the delicate balance between the solar radiation coming in from the sun and the infrared heat radiating back out from the Earth into space.
And clouds are interfering with both directions of that traffic.
Drastically so. On one hand, clouds act like giant mirrors. Think about those low, thick stratus clouds we talked about.
The big gray blankets?
Right. But from space, they are incredibly bright white. They reflect a massive percentage of incoming sunlight straight back out into the void before it can ever reach the surface to warm the planet.
So this reflection provides a huge net cooling effect on the globe.
Exactly.
Okay, that part seems straightforward. More mirrors equal a cooler planet.
If only it stopped there, right? But on the other hand, clouds also act like blankets.
Blankets?
Yeah. High, thin clouds like those wispy ice crystal cirrus clouds, they're too transparent to reflect much incoming sunlight. The visible solar energy just passes right through them. But they are highly effective at absorbing the invisible infrared heat that the warmed Earth is trying to radiate back out into space.
Wait, I have to push back here. Cirrus clouds are made of ice? How can a cloud made of literal ice act as a warming blanket?
It's a great question, but it isn't about the physical temperature of the ice itself. It's about the molecular structure trapping radiation.
Oh, I see.
Because they are so high up, they absorb the outgoing heat from the Earth, but they are too cold to effectively radiate that heat away into space. Instead, they trap it and re-radiate a portion of it back down to the surface.
So they act exactly like a greenhouse gas.
Exactly. This creates a net warming effect.
This is maddening. So clouds aren't just a simple thermostat dial we can turn up or down. They are constantly fighting themselves, some cooling, some warming, all at the exact same time across the globe.
Yes. And the complexity only deepens when you realize humans are actively altering this thermodynamic tug of war.
By accident, presumably.
Entirely by accident.
Let me guess. This loops back to the condensation nuclei, the invisible dust scaffolds.
It does. Human industrial activity, our factories, power plants, massive diesel engines, it pumps billions of fine aerosol particles into the atmosphere every single day.
Oh, wow. So we are essentially injecting the sky with a massive surplus of artificial condensation nuclei.
Precisely.
We're giving the water vapor more scaffolds to grab onto.
Yeah.
But wait, if the overall amount of water vapor in a specific air mass stays the same, and we just add a ton more dust, doesn't that just mean the same amount of water gets divided among a whole lot more seeds?
That is the exact mechanism. You nailed it. The resulting cloud is composed of significantly more droplets, but each individual droplet is much, much smaller than it would be in pristine air.
Okay, but why does the size of the droplet matter to the climate? It's the same amount of water.
Surface area. A cloud made of millions of tiny droplets has vastly more surface area than a cloud made of a few large droplets.
I'll get it.
And that increased surface area makes the cloud significantly brighter and more opaque. It becomes a much more effective mirror, scattering that incoming sunlight way more aggressively.
So our pollution is accidentally creating super mirrors. That's staggering.
It really is. And you can see the undeniable visual proof of this from satellites.
Really, like you can just see it.
Oh, yeah. When you look at satellite imagery of the oceans, you can often spot what meteorologists call ship tracks.
Ship tracks.
Yeah, these are long, brilliantly white streaks cutting through otherwise dull gray marine clouds, and they perfectly trace the commercial shipping lanes.
So the exhaust from the ships is making the clouds brighter.
Exactly. The diesel exhaust from massive cargo ships acts as this localized injection of condensation nuclei, instantly brightening the clouds directly above their path.
Okay, let's pull all of this together because my head is spinning a bit. Every single cloud is doing something completely different based on its height, its thickness, whether it's made of ice or water, and whether a cargo ship just happened to sail underneath it.
Right?
How on earth do climate scientists program that chaos into a computer to predict global warming?
It pushes the absolute limits of computational physics. I mean, to understand the challenge, you have to look at how global climate models actually operate.
Okay.
They essentially wrap a digital 3D grid around the entire Earth, and supercomputers then calculate how heat, wind, and moisture transfer from one grid cell to the next.
Like breaking the atmosphere down into a giant Rubik's Cube.
A Rubik's Cube where the individual blocks are massive, yes. Because the Earth is huge, a single grid cell in a global climate model might be tens of kilometers wide and tens of kilometers tall.
Oh, I see the problem immediately. A single cumulus cloud might only be 1 or 2 kilometers wide. It's way too small for the grid.
Far too small. It sounds absurd given modern technology, but even our most advanced supercomputers do not have remotely enough processing power to simulate the fluid dynamics of every individual cloud on the planet.
It's just too much data.
The scale is computationally impossible. We simply cannot simulate the microscopic physics of water vapor condensing on dust across the entire globe simultaneously.
It sounds like trying to describe every single individual pixel of a massive 4K movie. But you're only allowed to use a giant broad paintbrush.
Yeah,
You physically cannot paint the fine details.
that is an excellent analogy. So, since they can't paint the individual clouds pixel by pixel, scientists have to rely on what are called parameterizations.
Parameterizations. Okay, let's define that. How does a parameterization act as the giant paintbrush?
Well, a parameterization is essentially a simplified mathematical rule. So instead of asking the computer to build a cloud droplet by droplet, the scientists write a rule that says, look at the average temperature and humidity of this massive 50-kilometer grid cell, and based on those broad conditions, approximate how many clouds would probably be there and estimate their net effect on the sunlight.
So they're incredibly sophisticated, educated guesses.
They are heavily researched approximations based on vast amounts of real-world data, yes, but they are still approximations. And because different scientific teams around the world construct these mathematical rules slightly differently, their climate models produce slightly different predictions about how clouds will behave as the Earth continues to warm.
Because if the Earth warms, the atmosphere changes, which means cloud formations will inevitably change too.
Yes, and this creates a massive feedback loop. Will a warmer world create more low, thick clouds that act as mirrors and dampen the warming? Or will it create more high, thin clouds that act as blankets and amplify the warming?
It's terrifying not to know for sure.
This phenomenon, known as cloud feedback, is the single largest source of uncertainty in climate science today.
So what does this all mean? When we read a headline saying global temperatures might rise anywhere from 2 to 4 degrees over the next century, a huge portion of that gap exists simply because we can't perfectly predict what the clouds are going to do.
Exactly. It is a primary driving factor behind that margin of error. And this highlights a really vital aspect of scientific honesty.
How so?
Well, the foundational physics of greenhouse gases trapping heat. That is settled certainty. It has been understood as basic physics for over a century. The honest, actively researched uncertainty lies entirely in the hyper-complex, chaotic reaction of the clouds to that initial warming.
Right, but uncertainty isn't an excuse to throw our hands up and just stop trying.
Oh, far from it. The global scientific community is actively attacking this puzzle from every conceivable angle right now.
What are they doing?
We deploy fleets of satellites to continuously measure cloud albedo or reflectivity across the oceans. We fly specialized research aircraft directly into storm systems to measure droplet sizes and dust concentrations in real time.
Wow.
We even run ultra-high-resolution computer models on very tiny local patches of the sky to better understand the microphysics, hoping to improve those parameterizations for the massive global models. The gap is narrowing every single day.
It is genuinely incredible. I mean, we started this deep dive by just looking at a lazy, puffy white shape in the sky, and we followed the invisible water vapor as it desperately seeks out microscopic specks of sea salt. We watched it cool down by expanding in a drop of pressure, shaping the skies based on the terrain below, and ultimately holding the entire future of our climate models in its delicate balance of mirrors and blankets.
It forces you to realize that nothing in our atmosphere is truly passive. Every fluffy shape you see up there is a visual readout of invisible, incredibly powerful thermodynamic forces.
It really is. So to you listening to this deep dive right now, the next time you look out the window at a flat-bottomed cumulus cloud or you feel the mist of a morning fog bank against your face, remember that you aren't just looking at the weather. You are watching the invisible, hyperactive mechanics of the planet's entire energy budget happening in real time.
It completely transforms a mundane commute into a front row seat to the most beautiful confounding puzzle in Earth science.
It does. And I want to leave you with a final provocative thought to mull over. We talked about how human diesel exhaust is already unintentionally creating bright ship tracks over the oceans, forcing clouds to reflect more sunlight away. Well, if we were already accidentally building super mirrors, what would happen if we tried to use this exact same dust-seeding physics on purpose? Could we intentionally deploy a fleet of ships to spray microscopic sea salt into the marine clouds to artificially brighten them, deliberately trying to cool down the Earth? The physics says it would work, but the global consequences of hacking the sky's thermostat. Well, that's a whole other puzzle for another day. Thank you so much for joining us on this deep dive.